Hey there, everybody. Welcome back. So, in this second installment on Bernoulli's principle, we want to really look at what happens to a fluid as far as the conservation of energy goes when it changes height, right, inside a pipe. Keep it in mind the previous video about the continuity equation, okay? So that assumes that the volume of fluid, right, being displaced through, say, this first section of the pipe is the same as the volume being displaced in the second over here, right? And so in so doing, I've drawn the speeds such that they're decreasing from 1 to 2, right? The speed at V1 is faster than at V2 because 1 has a smaller diameter than V2 does, okay? So let's think of what's happening here. So on average, the height of the fluid going from 1 to 2 is changing, right? It's increasing, it's going up. So as far as the energy goes, for say one particle or one water molecule, we might say that the potential energy is increasing, right? So let's say the change in U is positive, right? It's increasing. Whoops. Because the potential energy is increasing for that water molecule, its speed is then decreasing. All right, and so now remembering back to hydrostatic pressure, which in essence is the pressure of the fluid on its container walls acting perpendicularly, right? When it's going from place 1 or I guess section 1 to section 2, that pressure is increasing, okay? Because let's think about what's happening. If you think of the particle, say, I don't know, particle here, right? It's primarily moving horizontally to the right. It's mostly moving this way, right? Yes, it might interact with its neighbors and bounce off of the wall, right? So it could bounce up and go this way and bounce back down. But for the most part, the molecules are moving pretty quickly to the right, okay? So they don't really have time to bump into their neighbors against the side of the wall. However, there is some pressure, okay? There are some contacts. However, there are much more contacts over here in section 2. Why? Well, they're not traveling as fast through the pipe, so there's more of a chance that they'll bump into their neighbor, right? Because their neighbors aren't moving as quickly as what they were over here in 1, okay? So because they're traveling slower, they might even have less momentum, right? In fact, they do have less momentum to the right, right? And so the gravitational force on them lends itself being greater against the walls, okay? Not so much up, but definitely downwards. And so all of the interactions combined throughout this entire volume, on average, are such that the pressures and the forces outwards or perpendicular against the walls are greater for a slower moving fluid than for a more quickly moving fluid. So we can put that over here. Let's see, the pressure is, I'll say, low at this point, right? And over here, pressure's high. Again, the pressure is inversely proportional to the speed of that fluid, right? So going from 1 to 2, we have an increasing pressure. And we can write this in equation form. We can say, in essence, that delta K plus delta U plus delta P, all of those things are equal to some constant value. Okay? Written another way, we have delta K. We can essentially think of each molecule having some kinetic energy. But again, remember that we're talking about a volume of water here, all traveling with a same general speed. So that volume of fluid here has some kinetic energy. So the kinetic energy per volume is what is better used in this case. And same thing for the others. So written another way, we have 1/2 mv squared over some volume, right? Again, lowercase v, capital V. And then same thing for the potential energy, mgh per volume, plus the pressure per volume. And that's equal to a constant. So what is this really? Well, we can rewrite this once again as far as 1/2 rho v squared plus rho gh plus, plus, that just stays pressure. Actually, this is pressure up here. Let's look at the units, right? Let's see. 1/2 rho v squared. Well, the units for that are density. Well, okay. Energy per volume. What are those units? Well, it's pretty much joules per cubic meter, right? Which works out to be a Newton meter over cubic meter, and then we have a Newton per meter squared. And this is force per area, right? And that's a pressure. So each of these here is in units of a pressure, right? So another way to think of Bernoulli's principle and Bernoulli's equation, which by the way is this right here, is it's simply a conservation of mass written in terms of pressure, okay? And one last way, if you want to expand this out initially and finally, you can do all of this for initial and final. Final plus pressure final. This is, in essence, what it means such that the changes are equal to a constant. Okay, written it out such that we have the initial of each of those equals the final of each of these. That's what it means. So you'll see this applied to an example in the next video. All right, thanks for watching.